So I'd like to talk a bit about how we see optical capacity scaling to meet internet demand over the next decade or more. So an interesting article was published in January by Adil Saleh and Jane Simmons. Adil's program manager at DARPA. He made sort of audacious claim that the internet is going to grow, has to grow 1,000x over the next 20 years. How did he get there? Pretty simple, actually, just by taking 40% compounded annual growth rate over 20 years, you're going to get to 1,000x. But he went further and discussed, he and she, Adil and Jane, put forth a proposal for how we actually might get there, and some interesting things fell out. First of all, that their first factor of 3 was just using the capacity that's already there in the network today. An awful lot of capacity is actually there in the transport network and is unused because, or actually all the network that's unused because of inefficiencies. But the biggest factor is simply by increasing spectral efficiency on fibers in the optical transport network. And, oops, go back. There's about a 10x, at least a 10x there. And I think that's starting from a baseline of today's 40 gigabit per second per wave. Transport systems that put about 3 terabits of capacity, 3 or 4 terabits of capacity on a fiber. First we need to understand what the transport layer is. I think a lot of guys here, or people here, are focused on the IP network, where of course you got service routers and peering routers and all your core routers. But there's an optical, a whole other, actually 2 whole other networks that sit below that. First, an OTN network. That is there in a lot of cases, not all cases, but that OTN network is to, the purpose is to do sub-lambda grooming or allow you to do TDM multiplexing of smaller circuits onto the bigger wavelengths. And then, of course, the WDM network itself underlies that, and those black lines between routers are really going in and out of the transport network as it goes across the country or around the world. So how have we been scaling the optical transport network in the last decade and a half? Is really through WDM, and the network's been scaling simply by scaling up the bit rate per wavelength, but second by scaling up the number of wavelengths. And we've gone from 2.5 gigabits on a single wavelength to 2.5 gigabits on 4, 8, 16 wavelengths, 40 wavelengths, then up to 10 gigabits, and it's scaled up to 160 wavelengths in some cases today at 10 gigs or 40 gigs at 80 wavelengths or 100 wavelengths. How are we going to continue from here? Are we going to continue scaling up the bit rate per wavelength, scale up the number of wavelengths? Possibly a little bit of both. Actually, the number of wavelengths actually might come down, as I'm going to show here, but the bit rate per wavelength, or actually channel, or super channel, as I'm about to discuss, is going to go up. So it's interesting to compare optics to what's happened in all other forms of communication, wireless, microwave, cell phones, etc., even copper lines like DSL. And in these types of technologies, what we've done is increase the spectral efficiency, or the bits per second per hertz on those media through very advanced digital signal processing enabled by advanced silicon technologies. And today, through things like QAM modulation, very high order QAM modulation, we're able to get several, as many as 10 bits per hertz over those media. The optical world, we've started very low because of WDM. We've been able to, because of the incredible bandwidth of fiber, we've been able to increase just on a TDM basis, and then the number of wavelengths. And we've been on a very steep curve, and lately here we're starting to take advantage of the same DSP and VLSI technology in the network that's being deployed today. These technologies are starting to come into use to do things like electronic chromatic dispersion compensation and 40 gig and 100 gig coherent communication, which I'm going to talk about more. So since the advent of DWDM, we've been relying on a few key technologies or techniques. First is just intensity modulation. So we simply turn the laser on and off, basically, turn the light on and off. And then direct detection, you just impinge the incoming wavelength or light signal on a photodetector and directly get ones and zeros out of it. And with WDM, we've been having multiple wavelengths separated, and according to this ITU grid that provides a standard for the spacing between these wavelengths. Going forward here, the network that's being deployed now is relying on phase modulation instead of intensity modulation. We've learned how to modulate the actual phase of the light. And then coherent detection by beating the incoming signal with a local oscillator in much the same way that radio does. But we've still been relying on ITU grid to separate the different wavelengths. And that's going to be changing in the future. As we go forward here, we're going from simpler phase modulation up to QAM modulation. And we're going to be, instead of just using simple coherent detection, we're going to be using coherent wave combining and separation, which I'm going to talk about further, and moving to what's called gridless superchannels. So I'll cover. All right, so let's just look a little bit at advanced modulation formats. The metric of comparison for optics has always been the capacity reach product. There's always been a trade-off in technology between the distance you can go and the amount of capacity that you can put over that distance. And they have, in any generation, it has a rough constant that you can get to for that level of technology. And that sort of constant is now peaking out with the Polmux QPSK, or Quadrature Phase Shift King scheme that's being used today in the 40 gig and 100 gig per wavelength technology that's being rolled out. As we go forward and start implementing QAM technologies, 8 QAM and 16 QAM, and who knows, 64 QAM or higher someday, those technologies are going to give us more capacity, but because of the nonlinearities of fiber, it takes more power to get those additional phase states and higher order QAM. But that additional power, because of the nonlinearity of fiber, impacts the OSNR of it. And you're actually going to, as you use those technology, it actually decreases the capacity reach product, which is unfortunate. You can't just keep pumping up capacity without, unfortunately, taking a hit on the reach. So the nice thing about phase modulation is it's much more tolerant of fiber impairments like chromatic dispersion, polarization mode dispersion, nonlinearities, etc. And we can put more bits per symbol, more data onto the fiber. But as we increase the baud rate of it, of course, those impairments have always scaled with the square of the data rate or the symbol rate, which is leading us to, of course, using higher order QAMs. And the nice thing about the phase modulation is it uses this coherent detection, which enables the use of DSPs, very, very high, very powerful DSP technology. And the result of all these things is that today's 100 gig wavelength technology that's being deployed actually gets the same or even better reach than 10 gig and even 2.5 before it. But we have a problem. As we want to keep going forward, if we want to try to get to terabit waves and we want to increase the capacity on the fiber from 10-ish terabits, which 100 gig is going to give us, to 20 in the 20s or 40s or up to 100 terabits on a fiber, how do we get there? How do we get to terabit waves? First question we really have to ask is, do we really want a terabit wave, or is what we're looking for just a terabit on a line card? A terabit is a single installable unit, a single through. And I think the industry is reaching the conclusion that really that's what you're looking for, and that 100 gig per wave, or sorry, terabit per wave and higher is actually not going to be practical, as the following charts are going to show. So how is the coherent detection done? You basically take your wavelength coming in and you put it through this optical mixer circuit that separates the polarizations, it separates the phase states, it separates the wavelength. And it separates it into a number of different signals, and it takes as many as 8 photodetectors for each wavelength to get all that information and get it into the DSP through a bank of ADCs. So in previous generation technology with direct detection, you only had a single photodetector. Now it takes 8 times as many to decode a single wavelength. So that requires, well, obviously a lot more optical circuitry, which makes your optical circuits very complicated. It also now, though, enabled these ADCs. These ADCs are running at tens of gigasamples per second. It's just unfathomable how ADC technology has advanced here in the last few years. It used to be, gigasamples per second was hard. Now we're doing tens, 20, 30, 40 gigasamples per second with multiple bits, 6 bits per sample. So if you're using this A to D technology, if you wanted to do a terabit wave, what would it mean? First, this chart is showing a couple different things, actually. It's showing the bits per symbol that you're using as you go with the higher order QAM technologies, and the OSNR penalty. That OSNR penalty basically is what impacts your reach. If you're going up to 64 QAM, for instance, you're taking nearly a 9, 10 dB OSNR penalty that directly comes off your reach. So you want to be at a lower, like the QPSK, which is where 100 gig is coming out. But if we look at the symbols per second, the rate at which the ADCs have to run, if you wanted to do a terabit per wave, it's simply impractical. If you wanted to do a BPSK decoding or a signal, it would take 640, that's running at 640 gigabaud. And the ADC actually has to run at twice that rate for the Nyquist rate. And a trillion, more than a trillion samples per second is just simply going to be impractical anytime in the future. By 2014, commercial ADCs we think are going to be running at about 64 gigasamples per second. So even if you go to QPSK, you're still at 320 gigabaud or 640 gigasamples per second. Even up at 64 QAM, you're at 105 gigabaud or a couple hundred gigasamples per second. So it's clearly out of reach of where we think ADC technology is going to be. So clearly, we're not going to get to a terabit wave or a terabit signal through a single wavelength technology. Just electronics are just not going to get us there. So the industry, the optical industry, is there's pretty good consensus now that instead of a single wave, what we're going to do is use WDM type technology to have multiple waves that are grouped, or multiple channels that are grouped into what's called a super channel. And the super channel will be routed through the optical network the same way a channel or a wavelength was previously, but all the channels within the super channel all flow together, and they all get modulated with separate pieces of the modulator they'll show and decoded with demodulators, as I just showed. So what are the technologies going to make these super channels possible? In particular, it's the coherent wave separation and the gridless super channels that I talked about. So in the past here, when we've done direct detection for 2.5 gig, 10 gig, et cetera, we've used a wavelength demux to separate the wavelengths and take that wavelength and impact it on a photodetector, shine it on a photodetector. But the WDMs have had to have guard bands between them. Because of the way that they're literally physically separated, you have to have some amount of spectrum between each signal to keep them separate. Because even though you're on an ITU grid, each device through the network, whether it's the transmitter or the receiver or all the ROADMs and WSSs in between, they're all not on exactly the same thing, so you have some imperfection. And that imperfection, you have to compensate. The ISI that it would create has to be compensated by using these guard bands to separate them. When we go to local oscillators for coherent communication for 100 gig or 40 gig, we're still using the ITU grid and we're still using these WDMs to keep the signal separate. And the local oscillator is tuned to roughly the wavelength that you're trying to decode, the same wavelength that the WDM demultiplexer is giving you. So going forward here, we're using coherent detection to get greater reach. We're still staying on a grid-based wavelength demux architecture. And this is the current state of the art for what's being deployed today and over the next few years with 40 gig and 100 gig per wave. Going forward again, this chart is showing what these super channels are going to look like. Today, as I said, if you have each channel, if it's 100 gig, it's separated by these guard bands. That's that red space in the spectrum there. That's wasted space. And there's roughly 25%. If you're sending a terabit with 10 channels at 100 gig each, roughly 25% of your spectrum is completely wasted because of these guard bands. So with coherent wave separation, we're doing things a little bit differently. The bottom left shows instead of those guard bands, we're packing all the channels in the super channel much more closely together, and we're separating those through the use of the DSP technology. Through the coherent demultiplexer, you're separating polarizations and the phase states, as I said. You're beating it with a local oscillator, and that by the time it gets in the DSP, you're actually able to use the DSP to filter out the ISI from other signals and filter out one channel versus another. And it turns out that digital signal processing is a lot more accurate than using digital signal processing to separate the different channels is a lot more accurate than trying to separate them optically. So you're able to get that 25% back, basically, and pack them much more closely. Now, between the super channels, though, since you want to still route those with today's WSS or ROADM technology, you still need those guard bands. The question is, how big can that super channel be, and how much capacity do you want to route at one time? So how many channels do you want at which bit rate? Because of if you look, though, at the complexity of these coherent demodulators, especially when you get to super channels where you're demodulating a whole bunch of channels separately, it's really getting to be a very complex optical circuit. As I said, it takes 8 photodetectors for each channel. If you have 10 channels in super channel, all of a sudden you need 80 photodetectors just for each terabit super channel. That really tells you that you really need to have some sort of, it will really be economically important to have some sort of photonic integrated circuit technology to do that implementation. What does this now look like here? The WDM is now demultiplexing the super channels from each other, but each super channel is now coming into an optical demultiplexer circuit that's using one or more local oscillators to separate out the different wavelengths, sending it through this fairly complicated optical circuit that's literally pulling it apart into 80 different ways and putting those on 80 photodetectors, 80 ADCs, and into an incredibly complicated DSP. These DSPs are literally running at trillions, tens of trillions of operations per second. They're incredible uses of silicon electronic ASIC technology, enabled by basically Moore's law, but 28 nanometer silicon and things like that. So this just shows if you have a bunch of super channels, each one is being independently demultiplexed and processed. Now, what is the result of using these super channels? The curve that was before, where I'm getting more capacity but lower reach through QPSK, 8 QAM, 16 QAM, et cetera, it basically pushes that curve out about 25%. That 25% spectrum I get just directly feeds into, I can use that for more capacity now. Simultaneously, the other thing that's happening in the optical network is what was previously a 4-ish terahertz amount of capacity in the C-band is amplifier technology is being increased to get to about 5 terahertz, which gives you an additional 25%. So all of a sudden I've got 50% more capacity just through those techniques. This chart shows a PM QPSK transmitter. As you can see, it's also a pretty complicated optical circuit with a laser diode, polarization beam splitter, these super Mach Zender modulator structures that modulate both the intensity and phase of the light, the imaginary and real components of the phase states. Now, interestingly, though, as I was talking about there's this capacity reach trade-off between which modulation technique you want to use, whether it's BPSK, QPSK, 8 QAM, 16 QAM, et cetera. It's nice to be able to build all of those different modulation schemes onto one circuit. Okay? And if you're building out of discrete parts, you'd be tempted to build individual boards for each of those individual modulation schemes, and you just deploy the right board at the right time. A nice thing about photonic integration that people are looking at is it allows you to build all those different modulation schemes onto one optical circuit and then basically software select which one you want to use at one time. And since it's in an optical chip, a photonic integrated circuit, it's basically the same cost to get all those things. Much like DSL, where you can trade off what reach you're getting. It just dynamically trades off the reach versus the capacity and the number of carriers it uses, the bit rate, et cetera. Optics is going the same way. We're getting going to be having a dial or reach capacity capability where at the baseline might be a QPSK signal at 100 gig. You're getting a particular reach, particular capacity. If I want to get additional reach, for whatever reason, I'm going subsea across the Pacific or something. I can basically turn the knob, change my optical circuit, change the DSP configuration, get much more reach at reduced capacity. Or I can go the other way. I can dial up 8 to 16 QAM, get a lot less reach, but maybe it's a metro area link that I don't need the reach. I just need to go 10 kilometers down the road or 100 kilometers down the road, not thousands of kilometers down the road. And I can have that capability basically built into a single card that can do those different things. This chart shows that more graphically. Each of these signals is a terabit signal. And what you're seeing actually is the black portion is actually showing multiple super channels imposed on the same fiber. So it's many terabits across that fiber. But within the red box, each one is a terabit signal. And what we're doing is changing the number of carriers, changing the modulation format of each of those carriers to still get a terabit, but at different amounts of spectrum. And then that different amount of spectrum, we can put more or less of those super channels on the same fiber. So as a result, at a shorter reach for a QPSK, we get 12 terabits on the fiber. But at 16 QAM, if we want more capacity, we can get maybe 25 terabits per second across the fiber. All right. So what's nice, though, is that we can take those technologies, and because of the software programmability, we can use it on the same network that is being deployed today, or in future gridless networks that I'll discuss. So the QPSK signals, the simple non-super channel signals, are being designed for 50 gigahertz based ROADM technology today, and these super channels can be made to fit through there just by changing the programming. Or as I do the super channel and I implement gridless ROADM technology in the future part of the network, I can use less spectrum. But for different portions of the network, for different reaches that I need, I might use more or less a higher order modulation scheme, and it can all be compatible by programming the optical layer as I need. And to summarize here, we think that terabit waves, terabit channels are going to be happening in the form of super channel, and there's pretty broad consensus in the optical industry that that's the way it's likely to happen. But we believe that flexible modulation is going to be necessary to be able to trade off different reaches as you go. These super channels are going to be made up of very tightly packed wavelengths or individual channels. They're not going to be on the ITU grid because you need to be able to pack them much more tightly than the ITU grid. They're not at 50 gigahertz, they're at 20 gigahertz or something like that. But by having programmable optical circuits, programmable DSP technology, you're going to be able to get all these things on first today's network in a backward compatible mode that doesn't give you the extra 25%, but in a future mode as this gridless optical layer gets deployed, put out there. So, to make this all economic, to have this amount of programmability, it's probably one way to improve that is some of the industry is going to try to do that through individual discrete optical circuits. Other people are going to try to do it through photonic integrated circuits that are really going to enable better economics for that. All right, thank you. Any questions?
All right, any questions? Any questions?
Drew, hi, this is Vishal Sharma from Metanoia Inc. So you spoke about coherent modulation and coherent wave separation, right? And in the end also you summarized it. But I'd like one clarification. Somewhere towards the end you mentioned that you can, because of the programmability, you can use the super channel concept even today. And then of course as you move to gridless ROADMs, it becomes much easier to implement. So to what extent can you actually do it today where you do have the ITU grid? What kind of capacity increases can you get for a super channel versus what would be possible when you had a totally gridless environment?
Yeah, I think I misspoke on one of the slides near the end. With today's 50 gigahertz based optical layer, you can't use the super channel concept because you need each wavelength on a 50 gigahertz. Some people, like Infinera, actually combine two wavelengths at 25 gigahertz each, but can fit that through 50 gigahertz. But otherwise, to get to the true super channel, the existing ROADMs don't work because they've got that hard separation at 50 gigahertz.
Okay, great. So that's what I was looking for. So that means to go to the super channels, we eventually need a gridless environment where we are untethered from the ITU grid, right?
That is untethered from the ITU grid?
Yeah.
Yes, exactly.
Okay, thanks.
Okay, anybody else? All right, Drew, thanks very much.
All right, thank you, everybody.